Good morning everyone, and welcome to today's worked exam answer question. Today I am having a look at an alkanes question which has come from an AQA AS paper. It's the 2018 paper. And within this alkanes question we are being asked to think about combustion and cracking and free radical substitution to produce a halogenoalkane. So I chose this question because it's asking a few different skills within these first three parts of this question. So we'll dive straight in. And we're told in question 1.1 that alkanes can be used as fuels, and we're therefore being asked to give an equation for the combustion of heptane. And heptane isn't an alkane that we're expected to know the formula of, so they've given it us there, C7H16. And then the clue as to what type of combustion we have has been given there. So it says that we're using an excess of oxygen, so we would be expected to be able to go, okay, that means that we are going to get complete combustion occurring. As soon as we know it's complete combustion, we know what two products we're going to make. So I'll start by writing the unbalanced equation. So C7H16 is going to be reacting with the excess of oxygen, and the excess will be shown in the balancing numbers, so that doesn't change kind of how we write the O2 itself. And then because it is complete combustion, we're going to have enough oxygen to make both carbon dioxide and water. Had we have had a limited supply of oxygen, we'd still make water, but we'd make either carbon monoxide or carbon here. So once we've got to this point, it now becomes a case of balancing. And when we're balancing combustion equations, we always need to leave the oxygen till the end. We can do the carbon and hydrogen in any order. I personally do carbon, then hydrogen, then oxygen. That's the order that the different elements appear on the left-hand side. So that's kind of makes sense to me, but you could do the hydrogen first. So if we've got 7 carbons in heptane, that's going to make 7 moles of carbon dioxide. We've got 16 hydrogens in heptane, so that means we're going to make 8 moles of water, because we've got the 2 after the H in the water, and 8 times 2 is 16. Then we can count up our oxygen. So we've got 7 lots of 2, so we've got 14 oxygens here. We've got the 8 oxygens there. 14 plus 8 is 22 oxygens. So in order to balance out the oxygens on this side, we're going to need 11 moles of O2. 11 times 2 is 22. Fab. That feels like a lot for a mark. At GCSE you would have got a lot more marks for that. That's the reality, I guess, of this being an A-level question now. But hopefully nice and straightforward in terms of recognising the type of combustion, getting your products written down, balancing your atoms. Okay. Then it says heptane can be obtained from catalytic cracking of a different alkane, hexadecane, which is C16H34, at a high temperature. We have to identify a suitable catalyst, catalytic cracking, give one condition of catalytic cracking other than high temperature, and we can't say high temperature because they've told us that in the question. And then we have to give an equation for the catalytic cracking of 1 mole of hexadecane to produce 1 molecule of heptane, 1 molecule of cyclohexane, and 1 other product. So there's a lot going on in that equation. So we'll do the other 2 parts first. So the catalyst that we use for catalytic cracking is zeolite. Has a very large surface area, which is very useful. In terms of the condition, we will use a high temperature, which potentially feels a little bit odd when we're thinking about catalytic cracking adding a catalyst. We normally think about the catalyst bringing the temperature down, and I do believe it brings it down a little bit, but not sufficient enough for us to say, oh, the temperature is now low. But it does enable us to use a much lower pressure than we would be using in thermal cracking. So in thermal cracking, we'd be using a high pressure of about 70 atmospheres, Here we'll be using only a slight pressure, which means not quite just atmospheric pressure, but equally not anything ridiculous in the realms of 70 atmospheres that we use for thermal cracking. So somewhere between 1 and 2 atmospheres. So 1 atmosphere would be the pressure that we're experiencing kind of now, so slightly above room pressure. In terms of temperature, high temperature for thermal cracking, somewhere between 1000 and 1200 Kelvin. For catalytic cracking, it has come down somewhere between 800 and 1000 Kelvin. So we are still seeing that benefit, but 800 to 1000 Kelvin is still a high temperature. Now, when it comes to the equation, again, first thing I'm going to do is write the formula of everything in the equation. So we are starting with 1 molecule of hexadecane, which is our C16H34, and we're only making using 1 molecule of that. There's nothing that I need to add as any other reactant. With catalytic cracking, we are breaking bonds. It's an example of thermal decomposition, so we don't need to add any other reactant. Product-wise, we've then got 1 molecule of heptane, which we had the formula for given to us in part 1, C7H16. 1 molecule of cyclohexane. So the cyclo bit means that the 6 carbons are joined together in a ring, and if you're not sure what the structural formula is, you can always draw it out to make sure that you are happy with the I didn't mean structural formula, sorry, I meant molecular formula. So we're going to have 6 carbons because it's hexane, but because we're joining the N2 carbons together, it doesn't have the same general formula as a normal alkane. It actually has the same general formula as an alkene. It doesn't have a double bond, but by joining those N carbons together, we remove 2 of the hydrogen atoms. So that's going to be C6H12. We only make 1 molecule of that, and then it says that we are going to produce 1 other product. So now what we can do is figure out how many carbon and hydrogens we've got left. So 16 carbons we had originally, we've accounted for 7 plus 6 of them, which is 13. So I've got 3 carbons left. And in terms of our hydrogens, we had 34 of them originally. We've accounted for 16 plus 12, which is 28. 28 up to 34 means we need another 6. So that would be propene, C3H6. Okay, hopefully that all makes sense. Any questions, obviously, please let me know. Moving on to part 3, we're then told that alkanes can be used in free radical substitution reactions to produce halogenoalkanes. Now, we're not being asked to do all of the steps here. We're not having to do initiation, then propagation, then termination. We're only needing to give equations for the propagation steps in the reaction of butane to form 2-chlorobutane. Now, one of the things that I believe I've said in other free radical substitution reaction videos is that we have to be using structural formula here. And we always should be using structural formula with propagation steps. Ideally as well termination steps. But it's especially key in this question because we're starting with butane where we've got 4 carbon atoms and we are only substituting 1 of the hydrogens for 1 chlorine atom, and that's happening on the 2nd carbon. If we were to use molecular, we would have no clue whether we had substituted the chlorine atom onto an end carbon or a middle carbon, and we need to be able to show in our mechanism which hydrogen is leaving and where the chlorine is then being substituted onto. So it's especially important here because we have different options for where the halogen could substitute on. Same for propane. With ethane, not a problem unless we already have a halogen atom on there. And obviously for methane it wouldn't be a problem because there's only 1 carbon. But for butane here it's essential. So if we can see that we've got chlorine being substituted on, we can recognise, hopefully, and we wouldn't need to show this, but that the first step, the initiation step, would be breaking the bond in a chlorine molecule to give us 2 chlorine free radicals. That's what we're going to then use in our first propagation step. So butane in structural formula, CH3, CH2, CH2, CH3 is going to react with one of those chlorine free radicals made in the initiation step, and we are going to get the hydrogen on one of these 2 carbons being removed. Now it doesn't matter which one, because if we were to take it from this carbon here, that would be the second carbon counting from left to right. If we took it from this carbon, it'd be the second carbon from right to left. Because there's no other atoms kind of already substituted onto the alkane, we don't need to worry about it being left or right. So I'm going to go counting from left to right. So we're going to remove a hydrogen from the carbon, so it's going to become CH. The rest of the butane hasn't changed. That carbon, having lost the hydrogen, will now have an unpaired electron, which we show with the dot like that. And the hydrogen that is coming off of the alkane reacts with the chlorine free radical to make HCl. And we always make the hydrogen halide in the first step of propagation. This new radical that we've produced, this alkyl radical, we take it into step 2. And this is where we always react that newly formed radical with a molecule of the halogen, and it has to be a molecule rather than a radical for 2 reasons. One, if it was a radical, combining 2 radicals together is actually termination, so it wouldn't then be a propagation step. But also, if we didn't use a chlorine molecule, we wouldn't regenerate the chlorine free radical, which would then kind of prevent the first propagation step from starting again, and we wouldn't get that chain reaction that we know we do get with propagation. So it has to be a halogen molecule, in this case Cl2, and in the second step we substitute the halogen atom into where it needs to go, so the chlorine going where the hydrogen originally was on that second carbon to give us our 2-chlorobutane. And then, as I said, the second chlorine atom will be a chlorine free radical, and that will then be able to restart step 1 off, and step 1 and 2 of propagation will continue to occur until all the butane's used up, all the radicals have combined together in termination. So hopefully that all makes lots of sense. If anybody has any questions, please do ask in the comments, or you can drop me an email. It's missg.tutoringandresources@outlook.com. Thanks so much for watching, guys. I really hope that you were able to take something from today's video.